So today we are going to talk about initial value problems, and I won't define it yet. We'll talk about a few things, but in general, I do want to talk about the fact that we might have some sort of function right here. I'm going to call this, say, y of t. And if we have some sort of function, well, we can do numerical integration. And that's going to give us, some sort of area under the curve. But there's something else that can get us this function, okay? And this is called, ODEs, or ordinary differential equations, okay? And what they come from is dy dt, or some sort of function, okay, that is slope information right here in some way, all right? And so we're going to talk about all the methods, okay, that can be used for solving ODEs. And one form, or one sort of type of problem for ODEs is called initial value problems, okay? And this effectively is that we know the initial point of some sort of function, but we don't know anything else. We don't know anything right here, or right here, or right here, but we do know something about the slope over that entire function. And so as a result, we can extract out what this function is over time using, okay, some sort of ODE solver. Okay, and so this is a class of problems, ODEs, that allow us, okay, to solve for a function, a profile. So the solution to an ODE, okay, is going to be a function, a profile of y, whatever the variable of interest is, over time or over space or what have you. So to give some examples of what ODEs are, and of course ODEs stand for ordinary differential equations, okay, mostly the world is modeled by differential equations, and even recently when we're talking about kind of the spread of COVID-19, they use differential equations to help them understand the rate of passing these diseases onto each other. But before we get onto those sort of topics, we have a couple of examples right here. For the first one, we have a spring mass damper, okay? So we have some sort of mass, all right? We have some sort of spring coefficient, and we have like some sort of damper, and the process of how a spring is going to oscillate back and forth or do some sort of damping process is governed by this equation right here, an ordinary differential equation. Okay, you can notice then that this is a second order ordinary differential equation, but effectively a differential equation has these derivatives inside of them, and they can be of course first or second or third or what have you. A falling parachutist, whoops, let me just redo that. A falling parachutist, okay, is only going to have one degree, or the first order. Okay, and of course you can recognize probably a lot of these things before. We have the mass of the parachutist, we have the gravitational constant right here, then we of course we have the velocity. Okay, that's going to be the dimension of concern or of interest that we have. And then we have some other parameters right here like c, okay, a factor, a coefficient of the drag associated with it. And of course, if c is big, well then of course this is going to be a larger term. And if it's much heavier, well, this is of course going to be a smaller term. And this is going to be kind of an impact of the drag, of how quickly or how much this parachutist is going to be slowed down. And then we also have swinging pendulums, okay? And swinging pendulums look very similar, okay, to the mass spring damper, because we have this m term right here, except we don't have x. We don't care necessarily about it going back and forth. We care about it going back and forth this way around some sort of point of rotation, and we are rotating about that point. And again, we're going to have some sort of other constants that will either slow it down or bring it back or what have you. So all of these are ordinary differential equations. Okay, and as I mentioned, sometimes we have second order ordinary differential equations, okay, because of course it involves second derivatives. And the good thing, or the good news, is that all these second and higher order differential equations, they can be reduced to just first order ODEs. And that's really nice because all the methods that we're going to talk about today are for first order ordinary differential equations, okay? And we can use these same ones for, the higher order ODE stuff that we're going to talk about as well later on. Okay, so how do we do that? Well, effectively, we take the original ODE, okay, and all we're going to do is we're going to substitute a small little substitution equation right here, y equals dx, okay, into all the higher order stuff right here, okay. And of course, this one is just replacing y, okay? So you can see that that is just becoming y. And then this term right here is going to become, well, dy dt. Effectively, if I have this equation, y equals dx dt, okay, I can take the derivative of both sides. I'm left with dy dt equals d dt, okay, dx dt, which is nothing more than, well, d2 dx over dt squared. All right, so we take all these equations, we plug them in, and then we're left with nothing more than a system, okay, of first order ordinary differential equations. Okay, here's the first one, and here's the second one. And so what we can do is that we can solve these together, and we never have to worry about the second order stuff from beforehand. Okay, so we're going to work then with ordinary differential equations with this type of form. Okay, we have some sort of slope information, I'm going to call it, okay, the first derivative, and there's going to be a function that returns, okay, that slope information. And once we have that slope information, well, then we can try to hopefully recreate the profile, okay, of y over time based upon the fact that we have some information about y, but not y itself. All right, so in this form, the previous example, okay, looks like this. Right, we've got one function. Okay, this is kind of our intermediate function, and of course we defined it as, well, y. Okay, so the function itself is going to return y. And the other function, dy dt, okay, there's that higher order second derivative, okay, is also defined, and here we have g, okay, a function of t and x and y, and in fact there can be other things right here. Is this minus cy plus kx divided by m, knowing and recognizing that this y right here, okay, is going to be kind of solved at the same time as this equation up here. So what this means then is that the slope information, or the first derivative, is a function. So we're going to use functions in today's lecture and in our Matlab examples. And so if we have second order ordinary differential equations, we're going to have, well, two slopes. We're going to have two functions, and we're going to have two first derivatives, okay, one for each order. All right, well, as I mentioned, we talk about these initial value problems, okay? We're going to focus on IVPs initially. Later on, we're going to talk about boundary value problems, okay? But that's going to be in the next lecture or next week. Today, we're just going to focus on IVPs. All right, and as I said before, we know something about the state of the system at the very beginning, okay? That's why we have this initial value going on. So if you recall, if we're trying to recreate the function, we know something about this point right here, okay? This is known. Okay, we don't know anything else about the shape of this profile. We don't know what it looks like. We don't know if it goes up or down, but we do know the initial value. And what we're going to try to do is use that function, that dy dt, okay, whatever that function was, okay, to learn something about that profile, to learn something about that function, okay? And effectively it comes down to a type of integration where we're going from dy dt all the way to y. And then, as I said before, with numerical integration on the first slide of this presentation, we can get the area under the curve by integrating yet again. All right, let's get back to what we're talking about. Often then, this independent variable, okay, is going to be time. Okay, that's what we have right here. But it could also be functions of x or something else. All right, but usually it's going to be something about time in engineering applications. Thus, then we can say we know something about the system at time equals to 0. So if we are dropping a parachutist, well, we know something about the vertical velocity when we drop him or her out of a helicopter, for example. The vertical velocity is usually 0, and so we can know something about y if y is the vertical velocity, okay, because it starts off at 0 right here, and then of course it might go up or down or whatever the way we have our frames of reference. All right, and then as I said, we're going to then approximate the differential equation, okay, numerically, to predict the system, okay, at some later time. So again, same sort of thing. We're starting with some sort of known value, and we want to know at a later time, okay, what is the velocity, or what is y, or whatever angle or variable of interest we care about, okay? All right, so later, of course, we're going to talk about boundary value problems, and these, okay, are usually going to be functions of the independent variable spatially, okay? So in this particular case, you don't always have t as it. Sometimes you might, okay, but you know something about the end state, which therefore it means that you usually have like x or something about the spatial information, okay, thus we know something about the initial point. We don't know anything about right here, but we know, okay, where it's going to end. So we have 2 points, known and known, right here. And we'll talk about that next week. All right, so what do we use? Well, we use our good old friend Taylor series in a method called Euler's method. Okay, so this is hopefully well understood, but we're building upon principles from previous lectures in the course, and of course recognize that this expansion point right here is found all over the place, and effectively we're using the Taylor series expansion to model some sort of, well, function, okay, at a whole bunch of different values of x using, as I said, the Taylor series expansion. All right, well, from previous methods we've used the first 2 terms, and today we're also going to use the first 2 terms, and we're going to expand it about this point of ti, which means then we set the expansion point to be ti. Effectively, okay, we're assuming then that we know something about maybe that first point, and therefore we set I to equal to 0, okay, for initial point. All right, so then here is effectively Euler's method, okay, and you'll notice then that we don't have an equal sign right here because it is an approximation. Okay, we replaced a with ti, and so we're looking at the first 2 terms from up above, these first 2 terms right here. So this first one is going to be nothing more than y ti, that's that initial point, especially if we set ti is equal to 0. And then we add on this value right here. This is the first derivative of y at time equals ti. And then again, taking a look at this term right here, we pop it down right here, okay, and it's going to be some sort of time differential. Okay, we're going to replace it with a delta t here in a second, but effectively it's the time difference between ti, our initial point, and our next time, ti plus 1. Okay, we take that summation together, and then we're going to get our next value of y. So effectively, again, we've got this point right here, okay, at time equals t0, and then we want to get the next point right here at time equals 1. Okay, and the process of going there, okay, is using what's called Euler's method. Okay, so Euler gets some credit all over the place, but effectively he's just using the first 2 terms of the Taylor series expansion. All right, well, you've probably already moved on to this shortened notation, but effectively, right, if we assume the subscript itself, okay, these little subscripts are representative of time, okay, then we don't need to kind of keep the ti, and then also we can kind of replace, okay, ti plus 1 minus ti, and assuming the time difference between each one of our time segments, which happens often, very similar to the numerical integration, right, we can set that to be just like a delta t. All right, so this is kind of in shorthand notation, but effectively it's the same sort of thing, and it's assumed then that we understand that this is just an approximation, and so we've even dropped that little tilde above the equal sign as well. Okay, and then of course in sort of modern English, right, we can go down here, and so we have some sort of old value, okay, maybe the current value, if you will, okay, and then we add a slope to some sort of step size, and that's going to give us the new value. So effectively up here we have a old value, we know some sort of slope information right here, and then we get the new value because we multiply that delta t times that slope information to get our new point right here. All right, but remember then, okay, that before we said we're going to work with ODEs of this form right here, dy equals ft or something like that. So Euler's method, okay, when we replace, okay, that dy dt with a function, it's going to have this in place of that, you know, y prime or dy dt or other versions of it. Okay, but there's very similar information right here, just shorthand notation, except now we're going to replace, okay, that one term. I'm going to go back up one slide. This guy right here down to that function of ti and yi. So then everything on the right hand side is known or is current knowledge about y. Okay, we know yi, we know yi, we know ti, and we know then how to call that function because that's given information, and of course we know the time difference between 2 values. And so what it becomes is that we just kind of march forward in time, okay, to try to get the next value of yi plus 1, and then of course we rinse and repeat. So again, everything on the left hand side is in the future or to be calculated for each next step. All right, so here's example number 1. All right, so we've got this differential equation, okay, it's a very easy one, but the slope information, the function itself, is nothing more than this minus y, okay? So here's the exact solution, all right? And if you have taken DiffEq classes, if you've taken ordinary difference equations in previous calculus classes and what have you, you should be able to know analytically, okay, how to get from this one to this one right here, okay? But we are going to do it numerically, okay? Just like in other methods throughout this whole semester, it takes a lot of table lookups, it takes a lot of additional calculus, it takes a lot of effort to understand how to go from here to here. Okay, and you'll be covering this as more so in future classes, in particular system dynamics. If you've taken DiffEq, you probably know how to work on this. Okay, in fact, in this particular case, you can integrate directly because you can isolate the term, but we're going to get into other functions that are much more challenging. So as a result then, numerically is a good sort of solution for engineers who don't have enough time to analytically solve for these ordinary difference equations. And in fact, since some of these equations get really complicated, all right, it's enough, since a computer can help you do these almost in real time and solve for the profile or for the function of y, given, right, that you have this dy dt for all time. So effectively then, this Euler method or approximation is going to be, well, same sort of thing. Okay, there's just two versions of it right here. We've got this function, okay? We're going to multiply it by delta t, and then we're going to add it to our value, our current value, and then we're going to get yi plus 1. Of course, I can be 0 right here, and this will result in y1. Okay, it's the same sort of thing where, because that function is nothing more than slope information, we solve for dy dt at all time. Okay, but since dy dt is given for all time, it's given as a function, we can make y be yi, and so therefore, okay, we're going to make this to be our equation in which we can pop into Matlab and figure out what yi plus 1 is for all time. And effectively, notice then that that function has been replaced with negative yi. Remember, that was up here. Okay, so then all I have to do is I have to march forward in time. Okay, starting off at y0, okay, and then going to, well, y1. And then I do the next thing right here, where I make this into y1 minus y1 delta t, and that's going to equal y2. And then I do the next step, y2 equals minus y2 delta t equals y3, and so on. All right, so now we're going to go to Matlab. I'm just going to walk through just this one slide, and then we're going to go off and we'll do this first example. But again, we've got the exact same ordinary difference equation right here. Okay, we're using Euler, and so we're going to replace that function with a specific function right here. And we're going to use an anonymous function and eventually, but I'm going to talk about the classic sort of function stuff. And then we're going to compare it with the exact answer right here. We'll see how good we are, and we're going to use these initial parameters. And so in an exam or in a homework assignment, I will have to give you kind of the initial time. Usually we start with times equal to 0, and the initial y value, and then some sort of value as to how long we should go for terms of time. Okay, and then of course this little dt value, this is the difference, okay, from up here. This is how large our step size is going to be, and we're going to kind of vary this dt to see kind of the resultant solution for different y's. Okay, and with that, I'm going to go off to Matlab and we'll start working this this example.